Hello and welcome to Euclide Academy. We offer science, that is physics, chemistry, biology, mathematics, as well as English online. And in this video, we're going to look at the science paper 1. We also do revise examination past papers. So let's go ahead and look at this exam past paper, which is basically for the General Certificate of Education, which was done in 2022. And I felt compelled to do this paper and look at the possible options or possible answers that we could have had, because revising past papers is one important thing that you can do before the exam, because basically you'll be facing the same questions. They'll just rephrase it in another way or write them in another way, but basically to be the same thing. So it's very important that you get used to the style of questioning that comes in the exam. So I would encourage you to start answering past papers as soon as you get settled, so that you get comfortable with the questions. That's all. So we'll look at question 1, which says, which of the following is not an example of a basic unit? So basic units, or sometimes also known as base units, we have about 7 of the basic unit, or also known as base units, and one of them is, of course, we have got meter, and then we have got for time, which is seconds. Then we have got for light, which is candela, or C. It is also a base unit. We have about 7 of them. So base units are said to be mutually independent, that they just come the way they are. And the second class of units is what we call derived units. These derived units come from the combination of 2 or more basic units. So you've got mass, and you've got seconds for time, then you've got candela for light, and then you've got Kelvin for temperature, then you've got kilogram as well. Kilogram for mass. So about 1, 2, 3, 4, 5. And what else do we have? We've got mole for amount of substance, and that should be about 8. So we've got a mole for amount of substance, so that should be about 6 of them. So these are called the base unit. And we also have ampere for current as a basic unit. So the only non-basic unit that we have here is watt. And watt is the only non-basic unit. The following diagram shows a broken rule used to measure the length of an object. So this is a broken rule used to measure the length of an object. What is the zero error and the actual length of the object? So first of all, I want us to look at the actual length of the object. So this object has got the rule has each unit has about 10 divisions, like 4, 5, 6, and from 4 to 5 you have about 10 divisions of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you are starting on this division here, which should be the 8th division. So this is 3.8.9, then 4. So the measurement of the object starts from 3.8, and then it goes all the way to 5.5, 0.6, 0.7, 0.8, 0.9 to 5.9. So the actual length of this one will be 5.9 minus 3.8, and that gives you 1, and that gives you 2. So you have 2.1 centimeters for the actual length, which is so basically, which eliminates B as not the correct option and eliminates D as the correct option. So now we have A and C, because they're the ones with 2.1 centimeters. So then we want to find out what is a zero error. So what is a zero error? Zero error, it is the error which is being shown when the true reading is actually 0. Okay, so for example, you want to measure something using an ammeter. You want to measure current, but then you find that there's already a reading there. If there's already a reading there, when there's nothing passing or no current passing, that is a zero error. So here we know that there's a zero error because there's already some reading. Okay, there's already some reading. Okay, so that is what we call the zero error. So what is the zero error here? So the zero error, we mentioned that we have 3.8 here, so it has to be 3.8, and that means, so it can be 4.2 because we already say we measured this side that is actually 3.8, so it can be 4.2. So the answer is, so at this point we've eliminated D because of 5.9, we've eliminated C because of 4.2, we've eliminated B because of 5.9. So that is a method you can use to answer past multiple choice questions. You can use the elimination method. It works pretty much great. So A will be the correct option here. A person dropped an orange from a basket on his head 1.8 meters to the ground. With what velocity does it strike the ground? Okay, so how you answer questions in physics, first of all, you collect the data, right? You collect the data. So here we have an orange falling from a person dropped an orange from a basket on his head. Okay, so if this was the distance, okay, his head 1.8 meters to the ground, so we have to the ground up to this point we have 1.8 meters. With what velocity does it strike the ground? So with what velocity does it strike the ground? So here we're talking about potential energy and kinetic energy. So we have the potential energy when the orange was on his head is equals to mgh, right? So the potential energy of that object was what was the mass, and we know that this potential energy is then converted to kinetic energy, right? So the value of the potential energy at this point will be equal to all of it will entirely be converted to kinetic energy just as the orange hits the ground, so they should be equal at the end. So kinetic energy, we know that it is half mv squared. So at the end of it all, these should be equal. So what we're going to say is potential energy, which is mgh mass, gravitational potential energy times potential pull times height, should be equal to half mass v squared, and then we can cancel this, we can cancel that, and then we have the gravitational field strength, G, which we usually take it as 10, and the value of G should be given as 10. So 10 times the height, which is 1.8, 10 times 1.8 is equal to v squared. Alright, because v squared divided by 2. So this will be 10 times 1.8, that is basically 18, right? Then 18 times 2, since we cross multiply here, we have v squared is equal to 36. Then square root of v is v square root of 36. We square both sides, so v is equal to 6 meters per second. This is velocity. Okay, so you have to be careful with the units. If, for example, they had said this was 18 centimeters, you have to be careful that you convert the 18 centimeters to meters. You need to use the best units when you are calculating. So this would be C. We'll go for C. Question 4. The following graph shows how the speed of a car varies with time. So we've got the velocity and time graph here. What was happening at the motion of the car between 10 seconds and 20 seconds? The acceleration of the car was, so this is a velocity time graph, and the gradient of the velocity time graph gives the acceleration, right? Gives you the acceleration. So if you know how to find gradient, you basically use the mathematical formula for gradient, which says that y2 minus y1 divided by x2 minus x1. It gives you the gradient. So on this graph, you can use this formula to give you the gradient, and that gradient that you find is actually the acceleration. So they are saying the acceleration of the car from what was happening to the motion of the car between 10 seconds and 20 seconds in terms of the acceleration. So you've got 10 this point, 20 this point. So what is the gradient here? So if you were to find the gradient here, it's actually 0. How? Because you say this is 20 comma 0, and then this is 10 comma this is 10 comma, I beg your pardon, this is actually 20 comma we have got some value, some y value right there, and 10 comma some y value right there here. So this is, if this was x, they will all be the same. So at this straight line, the gradient is equal to 0, because this would be x for this one. So meaning y2 will be x, y1 will be x, and you're going to have x minus x. What is it? It equals to 0. Okay, so the acceleration of the car was constant, not really, decreasing, increasing, 0. Actually it was 0. Question 5. A uniform plank is pivoted at its midpoint. 2 weights are added to the plank, 1 weight on each side of the pivot in the position shown in the following diagram. A vertical force is applied at an x to balance the plank. What is the size and direction of this force? Okay, so we want to find a vertical force which is being applied at an x to balance the plank. So basically, I encourage students, when you are answering questions, probably you should take 3 readings, or read the question 3 times to get the understanding. It only takes a few seconds. So the first reading just to get the idea, then the second reading just to for you to collect the data, the third reading for you to answer. So let's go through the second time. A uniform plank is pivoted at its midpoint. Okay, so this is a uniform plank. And then you've got the force here. 2 weights are added to the plank. Force here of 8 newtons, okay, down, and 12 newtons, okay, they're facing down. 1 weight on each side of the pivot in the position shown in the following diagram. A vertical force is applied at end x. So at the end we have got a vertical force. So what? Probably assume it should be here. Okay, shouldn't show the direction because we don't know. So it should be here. This is where the force should be. Okay, what is the size and direction of this force? Okay, so what do you think will be the size and direction of this force so that this is actually balanced? So here we use what we call the law of moments. The law of moments. This question is talking about the law of moments, which says that the sum of clockwise moments should equal to the sum of anti-clockwise moments for this to be uniformly balanced. So clockwise, you know, you're going like in this direction, and anti-clockwise in the other direction. So these moments should be equal for this to balance. So let us find the first of all, before we talk about the direction, let us find the size of this force by using the law of moments. So we can say this is, let's just look at the clockwise moments. So this is a clockwise moment, right? This on 8.0, and we know that moments, the moment is equals to force times the distance. Okay, the distance from the pivot to this point. So from the pivot up to here, you've got 8. You've got up to the 8 newtons. You've got 2 meters. So the moment at that particular point is 8 times 2. And then do we have another clockwise moment? I don't think so. I think this is the only moment we have. So this moment should be equal to the anti-clockwise moment, which is let's label it as x, because x is anti-clockwise. It forces this beam to topple the side. So this is anti-clockwise, and then that will be 8 times the distance from this point to the pivot is actually 2 plus 2, which is 4. So 4 times x, it will be 4x, plus the other moment we have is 12 here. 12 times the distance to the pivot is 2, okay, which is 12 times 2, and what we get is 24. I'm just going to write 24 here, so we get 24. So here you've got 8 times 2. What does it give you? It gives us 16. So 16, which is equal to 4x plus 24. So I'm just going to swap things here. I'm just going to get this 4x and bring it on the other side, so that we have 4x is equal to, okay, so probably we can just say, okay, so we get 4x is equal to, we have 8 times 6, which 8 times 2, which gives us 16, then negative 24. We subtract it from both sides. We have 16 minus 24, so 4x is equal to 16 minus 24. What do we get? That's negative 8. Then we divide both sides by 4 and that side by 4, so we have x is equals to negative 2. Okay, so we get a negative. So but this gives us the size, which is 2. So basically we can solve C and D, and then we have a negative value here. So if we have a negative value on 2, so now the question is what will be the direction? So if actually this is a negative value, then the direction should take us, okay, this side, upwards. If we take it upward, then it becomes a clockwise direction. If it is a clockwise direction, meaning we add it to this side, which was we had 16. So it basically we just use this to calculate the size. So it will be on this side. So if it was it would be 2 times 2 times 2 times 4 plus plus 8 times 2 should be equal to, so the 12 would be the anti-clockwise moment, which is 12 times 12 times 12 times 2. So if you calculate here, you're going to have 6 plus 16 right here, and then here you're going to have 24. So basically 6 plus 16 is 24, so 24 and 24 that side. So this perfectly balances this beam. So the size and direction, it should be 2 and upwards, which is B, using the law of moments. So question 5. The following diagram shows a small pickup weighing 5,000 newtons, okay, approaching a hill. It moves up the hill at a constant speed, okay, so that is the speed, and the distance is 200 meters up to this point, which is the vertical distance. The horizontal distance, and the vertical is 10. If the gravitational field strength is 10 newtons per kilogram, calculate the work done in moving the pickup up the hill. So we know that work is equal to force times the distance moved. So work is equal to force times the distance moved. So at this point, which distance moved are we going to use? So we've got 200 meters, this distance up to this point, and then from here up to there you've got 10 meters. So sometimes some information could just be there to confuse you. I don't know how these 200 meters could be applied. So here we use work is equal to what is the force? So the force we're going to use, the weight, is the weight of the truck, which is 5,000 newtons times. Remember, work is equals to force times distance in the direction of the force. So the weight of an object acts downwards. Okay, this is how your weight acts, and the weight of anything, it acts downwards. Okay, it follows gravity. So here we can't use this vertical distance, we use the this horizontal distance, we use the vertical one, which is 10. Therefore this gives us 5,000 50,000 joules, and we can put this in standard notation or basic notation as 5.0 times 10 with how many zeros? There are 4 of them. Okay, so it can be 1.1, can be 1.2. okay, can be, so it should be A. Okay, 5.0 times 10 to the power 4 joules. The following diagram, that is on question 7. The following diagram shows a simple machine. Okay, so it's a simple machine. We've got handles and we've got a wheel here. What type of simple machine is it? Okay, so what type of simple machine is this? We've got a handle and the wheel. Is it a gear? So basically this is not a gear. Is it a pulley? So you can remove the things that you know that, okay, these don't really make sense. Gear, no. Wedge is not a wedge, because a wedge you basically has to be something with sharp edge like that. Basically uses that shape, a triangular shape. Pulley is not a pulley. Okay, so it should be a lever. The following diagram shows boiling water and ice in a test tube. So you've got steam, you've got boiling water, you've got a test tube, and a wire gas and heat there, and ice cubes there, and you've got the wire gas there. What is the aim of this experiment? Okay, to show that heat can travel downwards, ice can melt in boiling water, steam is a good conductor of heat, water is a bad conductor of heat. Okay, let's analyze this experiment. You've got ice cubes down, and you've got a wire gas there, and you've got heat being applied to water, and the water is boiling. Then you've got steam. So in this experiment, what is the aim? So the aim doesn't necessarily have to be the truth. It's just the facts we want to find out, or myth we want to find out, or a theory we want to test. So is it that the water is a bad conductor of heat? Don't think so. Steam is a good conductor of heat? Don't think so. Ice cannot melt in boiling water? I don't think so. Heat cannot travel downwards. So we've got heat being applied on top of the ice right there, and we've got boiling water here, and the water is boiling right from the top, and then we've got the ice and the wire gas on the bottom. I probably see that this experiment designed to see if actually the ice cubes are going to melt. So I'll go for A. Heat cannot travel downwards was the aim of this experiment. Which of the following equation best describes Charles' law of thermodynamics? So Charles' law does that the volume is directly proportional to the temperature. The volume of a gas is directly proportional to the temperature. So I'll just put directly proportional to the temperature. So we'll just say T. Volume is directly proportional to the temperature. So if that is the case, then the formula can be written as V volume is equal to some constant K times the temperature. So basically we look at the variations of this formula in this question. Is it Vt is equals to K? Basically this is not a derived formula of this or another form of this. volume divided by T is equal to K. Okay, this seems right, like this formula, because we can divide this by T and divide this by T, and we'll cancel that, and that will give us that K is equal to V divided by T. So we go with V. That's the correct answer. 10. The following diagram shows thermometers used in a school laboratory. So thermometer T, U, V, and W. And which thermometer has the greatest range, and which thermometer has the greatest sensitivity? So greatest range and the greatest sensitivity. So this goes from 0 degrees Celsius to 20 degrees Celsius, 0 degrees to 40 degrees and above, 0 degrees to almost 200 degrees Celsius. Okay, this one has got 140 to 300. So which one has got the greatest range here? Is it 0 to 200? V, I think that will make sense, because 0 to 200, this starts from 140 to 330. When we subtract, we get something like a 160. So V should have the greatest range. So already we cancel C and D, and then which thermometer has the greatest sensitivity? So the battle is between U and T. So T has from 0 to 20 degrees Celsius, and then U is from 0 to 40 degrees Celsius. But we can look at the divisions. From 0, you have 0 up to 30. Okay, so which thermometer has the greatest sensitivity? From T and U, we can see that here starts from 0, then we go to 5. Here from 0, then we go to 30. So which is more sensitive? Well, so probably it's from 0 to 5 rather than 0 to 30. So I'll go for T and V. So the answer here is on B as the correct option. So we look at question 11. A wave of frequency 13,000 Hz travel 1,300 meters in 2 seconds. What is the wavelength of the wave? So basically this is on wave motion, and we know that velocity should be equal to frequency times the wavelength. And right here we have the frequency as 13,000 Hz. We multiply times the wavelength, which is R, and then they say this gives us velocity of it travels 1,300 meters in 2 seconds. So therefore that should give you the velocity. You can calculate the velocity by saying 1,300 divide by 2 seconds, right? Because the distance over time. This is the distance, this is the time. And get the velocity, which is the speed. In this case, just one and the same thing. So we divide 1,300 divided by 2. What do we get? So we have something like 650. So we should have 650. So now this will be meters per second. So this is the velocity, and then this is the wavelength. So it will be the wavelength, frequency times the wavelength, which is 13,000 times the wavelength, is equal to the velocity, which you found here to be 650 meters per second, right? Okay, then we divide this by sorry, not yes, just 13,000, not 1,300, 13,000 divide by 13,000, and here divide by 13,000. So you can confuse the two because this says 13,000, it says 1,300. So you might swap these, so don't make that mistake. So you remove this and then you cancel that. So we have the wavelength is equals to 650 divided by 13,000. So divide by 13,000, that will give you 0.05. Now with the wavelength, it's a length, and we're talking about meters here. So it's 0.05 meters, and that should be A. 12. A light travels from air into a glass block of refractive index 1.5 as shown in the point diagram. So we have this and that. Calculate the angle of refraction in the glass block. So when we talk about the refraction of light, you've got the incident angle and the angle of refraction here. So angle of incident here before it goes into the block, and then when it goes into the block, you got the angle of refraction. So this is your normal. This is the normal, and the angle in between these two is what we call the angle of refraction. Here it is known as the angle of incidence. So what is going to be here, we calculate the refractive index. How do you calculate this refractive index right there? So we calculate the refractive index by saying refractive index, just say R is equal to the sine of the angle of incidence as I divided by the sine of the angle of refraction as R. So incident they've given us to be 1.5, and then we say sine of the angle of incidence, which is 60 degrees, right? Is 60. Then you divide this by the angle of refraction, which is sine of R. And then you can multiply this. It will be sine of R times 1.5. So it will be 1.5 times this is equal to sine 60 degrees. Okay, then you divide both sides by 1.5. This is not 8, this is S, and this by 1.5. So this and that will cancel. So we find that the sine R is equal to sine 60 degrees divided by 1.5. So you need to be careful with your calculator. You need to be comfortable with the calculator. Start working around the calculator as soon as possible. So I'll probably be dropping some tips in the next video, on the other video, explain in some of the things you can do right to give you a chance to get the maximum points. So you can say sine of 60 on your calculator, sine of 60. So we get something like sine R is equals to 0.5773 and some values that is on your calculator. Then we find the inverse of this. We say R, the sine inverse of this, which is sine inverse of the 0.5773. So we get the answer as, so this gives us something like R, or put it here, is equals to 35.2 degrees, something like that. Okay, depending with how many decimal places you went there. I just went with 4. 35.2 degrees. So R should be 35. Should be 35. So it goes C. And then we go to 13. A person standing 150 meters from the front of the cliff claps his hands once and hears an echo after 0.9 seconds. Find the speed of the sound. So if this is our person right here, so it's really important to draw some figures just to help you understand. You're allowed to do this, so always do it. And that is 150 meters. And then he claps. Find the speed of sound in air. So sound leaves his hands as he's clapping, and then it goes to the wall, bounces back with an echo. An echo is just a bouncing back of sound, right? So bounces back, comes back here. So it travels this distance twice. So it comes back after 0.9 seconds. So find the speed. So speed is equals to distance over time. So speed is equals to distance over time. What is the distance? The distance is 150 meters times 2 because it travels back and forth, and that gives you 300. Divided by the time it took is 0.9. So we can say 300 divided by 0.9. What do we get? We get 333.333. So I encourage you to use a calculator along on this one. Uh, so 3333.333. Okay, so that will be D. So you don't really have to watch along without trying to get a hands-on experience, so or a hands-on practice. I would encourage you at least to find a pen and paper and then try to solve along or solve it your question yourself, attempt the question, and then once you feel like you've gotten the answer or you're stuck, you can play the video so that we do it together. So it's very important. You just don't have to watch without really taking part. So which of the following does loudness of sound depend on? So loudness of sound is about wave motion again. A higher frequency means there is higher pitch, and the amplitude means there is more loudness. So for this one, we go with amplitude. So we have the following diagram shows a small compass close to a magnet. So this is a compass close to magnet. So which is the direction? Which diagram shows the correct compass direction? Okay, so we have it's pointing to, actually this one is pointing to the south, north. Then it's pointing in the south direction, right? Because it's next to the North Pole, but on the North Pole, on the north side, there is pointing to the south. So this is actually pointing to the north, D. So D will be our answer. 16. A negatively charged rod is held close to, but not touching an insulated metosphere as shown in the following diagram. So this is the load and this is the metosphere. Which diagram shows the correct charge distribution on the sphere? So when it comes to charges, we know we've got the positive charges and the negative charge. We know that these repel, opposite charges repel, opposite charges attract, sorry, like charges repel. So if you have negative, the negative, they'll repel. So we expect this opposite, the opposite to these negative charges to be right here. You expect the opposite to the negative to be right here. So they'll be attracted to each other. So the negatives will be on the other side. So it should be B. Which of the following circuit diagram shows all the three resistors in parallel? So in parallel, we have this is in series. These not all of them are in parallel. Okay, not all in parallel. Actually, these in parallel. And then we can have D here. They're all in parallel. An ideal transformer has an input voltage of 12 volts and an output voltage of 240 volts. It has 2000 turns in its primary coil. Find the number of turns in the secondary coil. So we know that this is a step-up transformer because an output actually is higher than the input. So it's a step-up transformer. So for step-up transformer, we have that the voltage of the primary divided by the voltage of the secondary should be equal to the number of turns of the primary divided by the number of turns in the secondary. That is for step-up transformer. So this we can say we have voltage in the primary, a transformer has an input voltage of 12 volts and an output voltage of 240 volts. It has a 200 turns in the primary core. Find the number of turns in the secondary core. So here we're going to calculate the voltage in the primary. We have 12 volts. We have 12 volts, and then the voltage in the secondary we have 240, and then this we equate it to the number of turns in the primary. We have got 200, 2000, 2000, not 200, 2000 divided by the number of turns in the secondary. We just say ns. So we just cross multiply and we should have n s is equals to 2000 times 2000 times 240. That should be that should give us 480,000. Is 2000 times 240 should be 480,000. Then we divide this by 12. Divide this by 12 and see what do we get. So here we should get 12 into 8 is 4, into 48 is 4. So you have 40,000 number of turns. So 40,000 number of turns, and that should be on C. Which of the following radioactive emissions has the strongest ionizing effect? So the strongest ionizing effect, we've got X-rays, gamma rays, and beta. These are called form of radiations, and they've got different properties in nature. And to learn more, or if you want more lessons, we do have online lessons for you. You can join our online lessons, and we do talk about this, and we teach you on this, so to be very more straightforward. If you're comfortable with this, that is good as well. But if you further help, we have online lessons available for you. You don't have to attend physically. You just use your phone. We'll give you the application and everything and how to get started to learn with us. So the radio emissions which has the strongest ionizing effect, actually amongst all these, is the alpha. Alpha has the most ionizing effect. Radium has a half-life of 1600 years. Calculate the number of half-lives it will undergo for a 100-gram mass to reduce to 12.5 grams. So half-life is the number of years it takes for half of a radioactive substance to reduce, or to disintegrate. The number of years it takes for half of this for this to come to half is what we call the half-life. So if you have got 100 grams, right, and half of that is 50 grams, right? So half-life is the number of years it took for these 100 grams to come to 50 grams. So here they're saying it is 1600 years. Again, we can reduce this to go to 25, right? So divide by, so this, again, this is another half-life, and that will be, again, you can go like that, 25 divided by 2, and that gives you 12.5. Okay, that's 12.5. Okay, this is the final grams. So from 100 you go to 50 grams, that is one half-life, right? From here you go to 25, again that is one half-life, and from here you go to 12.5, that is one half-life. Okay, so we have got 3. Okay, so we come to section B. Answer all questions in this section. Write your answers in the space provided in this paper. So figure 1.1, B1.1 shows a simple pendulum suspended on a clamp stand for determining the periodic time. Okay, so go from A to B to C. What is meant by periodic time of a simple pendulum? So this is the time taken for one complete swing or oscillation of a pendulum. So it's the time taken for one complete swing or oscillation of a pendulum. That is the periodic uh, swing, the periodic time. So time, that is the period or periodic time of a simple pendulum. The time taken for one complete swing of a pendulum or an oscillation. Two factors that do not affect the period of a pendulum. So number one is the mass of the bulb. The mass of the bulb does not affect the period of the pendulum. Mass of the bulb, and then we have the size of the bulb. Size of the bulb, or the shape of the bulb. Okay, or the material of the bulb. Okay, so these do not affect the period of a pendulum. This experiment is done on Earth, and repeated on the moon. Where would the periodic time be higher? So the periodic time will be higher on the moon. Just file your answer. Okay, because um the gravitational field strength, or the acceleration due to gravity uh on the moon, it is lower than that on Earth. Hence, you have more time taken to complete an acceleration on the moon than on the Earth. So the periodic time will be higher on the moon. Hope you get that explanation. So the G in this case, but if you're writing, you have to specify this is the acceleration due to gravity. When you go to the moon, is lower than that on Earth by about 0.016 something. So it's lower than that on Earth. So hence on the moon, it will be the period will be higher. So G is lower on the moon than on Earth. So that's the reason why it will take more for when you're on the moon than when you're on Earth. And in the coming weeks, just an announcement that we'll be releasing our on Android as well as iOS application. So hit the like button in the notification bell so that when the application is ready, you can be one of the people that gets to download it. We'll release the application, the e-learning application, to you so that you can get to download. So don't forget to subscribe and hit the notification bell, so once we have the application ready, we will launch it here and you can get to download. Be one of the very first people to download the e-learning application. It will be a very fun application. Basically, it's just to give you more materials, more videos, more lessons, and just to give you more information, more content. The B2 2.1 shows an apparatus a learner used to measure the mass of an irregular object. So take G to be 10 newtons per kilogram. Now this is 350 grams irregular solid, and this is the balance, being balanced. What is the weight of the irregular solid? So what do you think is the weight of the irregular solid? So weight is a force. Weight is equal to mass times acceleration due to gravity of the gravitational field strength, and mass of this a regular solid is 350 grams. Now, remember I said you have to be careful when dealing with numbers. You have to put them in their base unit, the basic units. You divide this by 1000, so it will be 0.35 kilograms. So 0.35 or 0.35 is the same times J, which is 10, and that should give you 3.5 newtons. Okay, so to be 3.5 newtons is the weight.
The learner measured the weight of an object on top of Mount Everest and also down the same mountain using a spring balance, and also down the same mountain using a spring balance. What was his observation about the two weights? So the weight on top of Mount Everest was lower than the weight which was measured down Mount Everest. So this is what we would put, or we would say the weight of an object is more at the bottom of Mount Everest than at the top. Give a reason for the learner's observation. Well, this is because the higher you go, the less gravity you have, the less the pull of gravity on that the mass of that of the object or whatever that you're measuring. So therefore, you're going to have less gravitational pull as you go higher, compared when you're down. The gravitational pull will be greater. So we can express this as, so we can basically say gravity decreases with distance. So at the top of the mountain is further away from the center of mass of the earth than at the bottom. So we expect the weight of an object to be more at the bottom of Everest than at the top.
Question C says, find the force X acting upwards at the pivot. So if we look at our seesaw here, we have got the pivot X. There is a force pointing upwards, like acting in the upward direction, and then we have other forces here. So how we can find the number of forces which are acting on this pivot or on this pivot? You've got about downwards forces, and upwards forces. So these forces, they're moving in the vertical direction. So they're all vertical forces, right? And then what we have here is a seesaw which is perfectly balanced, so to say, and it's not moving. So meaning, if it's not moving, then the forward forces and the backward forces, the upward forces and the downward forces have to be the same, or it means they have to cancel each other. They have to give you 0. So if we say we have got this force is 200, so if you add all these forces and you subtract them from X, they should give you 0. They should cancel. So X should be equal to this is the only upward force here, right? It's the only force acting upwards, is equal to 200 newtons plus the 150 newtons plus the 110 newtons. So this should give you X is equals to 200, which is 310, then 310, which is 46. So 460 newtons. So X, the force should be 460 newtons, which is the upward force on this. So we put it on part C. So this is the force X is 460 newtons according to how we calculated it at the top there. And we got the next question. A brick, B5, a brick fell from a building under construction. The brick fell from a height of 80 meters. Take J to be 10 newtons per kilogram. Calculate the potential energy. So as I said, you can draw a bit of diagrams to help you. So we have a brick right there at the top, and then this one uh has got mass of 8 kilograms. Then it fell from a building under construction. The brick fell from a height of 80 meters. So this height here is 80 meters. Take G as 10. Calculate the potential energy. So what is the potential energy right here? Just before it started to fall. So just right there at the point as it's falling down, what is its potential energy? So as we said earlier in part A, we said potential energy is equal to mass times gravitational field strength, or acceleration due to gravity, times height. So the potential energy here will be uh, the mass of the brick, which is 8 times the gravitational field strength, which is 10, times the height, which is 80. Okay, so that should give us 8 8 times 80, then you multiply by 10, you get somewhere around 6,400. So 6,400 joules. After falling halfway down. So what is the gravitational potential energy after falling halfway down? So after falling halfway down, then this gravitational energy, there are two ways. It should probably be half of this. Okay, so it should probably be of the half of the 6,400. That point, since the height is now half, and that should give us 3,200 joules. Or if you make the height there to be 40, since it's halfway, instead of 80, you're still going to get 3,200 joules. Calculate the kinetic energy of the brick after falling for 3 seconds. Okay, calculate the kinetic energy of the brick after falling for 3 seconds. So um, kinetic energy is equal to half mass times velocity squared. Right. So we have the mass, and what we want is we want to find the velocity. We don't have the velocity, we have the mass. So how can we solve this question? So we need to find the velocity. So after falling for 3 seconds, what will be the velocity? Um, so they've given us 3 seconds. We can find velocity, final velocity. You can say the velocity, final velocity is equal to initial velocity plus acceleration times t. Okay, and then we can say this one, initial velocity was 0. It started from rest because it was at the top here. So for 3 seconds, we had a final velocity after 3 seconds. So we can use this formula to find that final velocity, and then we can say final velocity is equal to initial velocity, which is 0, plus acceleration, which is 10. Acceleration, we can use acceleration due to gravity, okay, as 10, because it's a downwards force, so we use 10, and then we can use the t for time, which is 3 seconds, and then the final velocity, what we get is 30 meters per second. That is the final velocity. So after getting the final velocity, we can use it here. We can say kinetic energy is equals to half the mass of the brick, which is 8, times the final velocity, which is 30. We square this, and then this will be 4 times the square of 30. And what do we get? 4 times 30 squared, we get 3600. So we get 3600, so 3600 kinetic energy, so joules. Okay, 3600 joules. Basics, what is boiling? So we can say boiling is the process of converting liquid into vapor, and definitely it happens at the boiling point. So it's just a process of converting liquid. It converts liquid into vapor. Of course, you can expand the sentence. I'll leave that up to you. The process of converting liquid into vapor, and it happens at the boiling point. Okay, it's a very simple thing. So boiling is the process of converting liquid into vapor. Like you have water in a pot, you boil it, and then it turns to vapor. Okay, so that is boiling. Sets of factors that affect the boiling point of a liquid. So what factors that would affect the boiling point of a liquid? So the two factors that can affect the boiling point of a liquid, um, we have the purity of the substance, whether the substance is impure or not, so it has got particles in it that can affect. And we can also talk about the atmospheric pressure. Atmospheric pressure. We can also talk about vapor pressure and even temperature. Can even include temperature. So these factors can affect the boiling point of a liquid. Explain two differences between boiling and evaporation. So one could be that boiling happens at the boiling point. So it's a specific temperature. For example, water boils at the temperature, but no one knows at which point water evaporates. So evaporation happens at doesn't have a specific point. So it just evaporation happens at any point or any temperature, while boiling happens at the boiling point. Evaporation at the boiling temperature. Then boiling happens on the boiling happens throughout. Boiling happens or occurs throughout the liquid. Okay, throughout the whole liquid. And evaporation happens on the surface. Okay, it starts from the surface. Evaporation happens on the surface. Starts on the surface, and then the down molecules, water molecules, or whatever liquid molecules follow. So it happens on the surface. So that's it. Those are the differences. And then, okay, we come to day 7. Shows figure 7.1 shows the brightness of the electromagnetic radiation with different wavelengths. Okay, so with different wavelengths, we have got different brightness. This is the brightness, this is the wavelength. Then from the graph, determine the wavelength where the radiation is brightest. So where is radiation brightest? So we've got at this point, or is it at this point? So this we can see that it's not here, it is somewhere here, and here it is somewhere there. So it should be at 1.0 times 10 to the power negative 6. If the wavelength of the visible light rays are between 4.0 and 7.0 plus 4 to the power 10 negative 7, what is the name of the radiation in A above? So if the wavelength of which we are talking about has got light rays between 4 visible light rays are between 4 and 7. What is the name of the radiation in A above? So this question is basically focusing on the electromagnetic spectrum. So you've got the spectrum aligns all the radiation depending on the wavelengths. Okay, so you've got the gamma rays, then you've got the X-rays and ultraviolet, then you've got light waves. So if light starts between 4.0 the power 7 and this is 1.0, so what is the name of the radiation in A above? So it should be any of these, which are the side which, if this is 4.0, then it could be, we can even put gamma rays, because gamma rays on the spectrum are like on the far to the left of the spectrum, so expect this to be to the left. It'll be gamma rays, or maybe we can even say X-rays, because it's not that much specific. Okay. Calculate the frequency of the radiation in A. Take speed of light as 3 times 10 meters a second. Calculate the frequency of the radiation in A. So the frequency of this radiation. Okay. So frequency, we know that the speed of velocity is equal to frequency times the wavelength. Okay, so we can use the speed of light. So the wavelength will be the speed which is given us, which is 3 times 10 to the power 8 divided by the we want to find frequency, not the wavelength, actually, and the wavelength. So the frequency will be the speed, which is 3 times 10 to the power 8 divided by the wavelength, which, what is the wavelength that we have in A? So it is 1.0 times 10 to the power negative 6, because they say the frequency of radiation A. So what does this give us? So this gives us a frequency of about 3 times 10 to the power of 14 hertz. So that is the frequency. This has got that frequency, and probably this frequency is somewhere around the ultraviolet. So ultraviolet will be the best option here. So you can even go back and try to correct things. So we can go with ultraviolet on this one here. So one use of the radiation in A above. So what could be one use of this radiation? So they're used as disinfectants for killing microbes, germs. So they're used as disinfectants. So they're used as disinfectants. And then we go to pH. Figure 8.1 shows bar magnets with different poles. So P, Q, and R, B, T, Y, W. Identify the following poles. Okay, so we know unlike poles attract, like poles repel. So identify the following poles. So these two, P and Q, are attracting, right? So we can say this is north, then this will be south. So if this, then we have, if, oh, another way we can use is the magnetic flask moves from north to south, like they come from north to south. So um, so these lines they represent the flask, so they're coming from north to south. So let us change this to be the other way around. So this where the flask is coming, this will be south. So if this is the south, that should be the north. Okay, that way. And this also will be the south, and that will be the north. Okay, they're coming from north to south, and that also should be the north. That should be the south, which gives us this as the opposite, the south. So P is the south, R is south, T is north, and Y is north. So why we pick this? Because we're using the direction of the flask, a magnetic flask. These are these imaginary lines. These lines run from the north to south. So they're coming from north to south. And we go to figure B, to question B9. Figure 9.1 shows a circuit consisting of a 12-volt battery with a combination of resistors between X, Y, and Z. Calculate the effective resistance between Y and Z in the circuit. So here we have our circuit. We have our X, Y. So we're saying that this circuit has got a battery with a voltage of 12 volts. Okay, so that is the voltage with the combination of resistors between points X, Y. This is a resistor, that is a resistor, that is a resistor. And calculate the effective resistance between Y and Z in the diagram. So what is the effective resistance? So the effective resistance between Y and Z. So we've got X, Y, and Z are points, not really resistors. They are points. So this is a resistor, that is a resistor, that is a resistor. So the resistance, effective resistance between point Y and Z. So these are in parallel. So when you're finding the total resistance in parallel, we calculate it in this form. So total resistance will be 1 divided by resistor 1 plus 1 over resistor 2. So which means the total resistance here will be 1 over resistor 1 is 1 over 6 plus 1 over 1 over 12. And then this should give us 1 over R. Total resistance is equals to, and here we get 1 over 4. So this gives us 1 over 4. Now remember, this is not the answer. We need to find RT, so which means we just find the reciprocal of that, or cross multiply, and we get RT, or total resistance or effective resistance, is equals to 4 ohms. Find the current through the 2 ohm resistor. Okay, what is the current there? So we know that according to Ohm's law, voltage is equal to current times resistance, right? So here find the current through the second the 2 ohm resistor. So we find the total resistance in the circuit so that we can find the total current. So which is the same current through the second the 2 ohm resistor. So we have the resistance between Y and Z. It is 4. The effective resistance, it is 4. and then we have the total resistance would be 4 plus the 2. So 2 plus 4. So total resistance in the circuit would be 6 ohms, and that will mean that the current is equals to the voltage, which is 12 divided by the total resistance, which is 6, and then the current will be 2 amps. That will be the total current in the circuit. So calculate the voltage across the 2 ohm resistor. So voltage is equals to current. So the current is the same, is 2 times the resistor. So the resistance is 2. So the voltage is equals to 2 times 2. We have got 4 volts. Okay, so that is how we calculate this. So we're remaining with section C, and at this very point, we do have online lessons for those who would want to join these science classes. You want to learn more, so you can send the message to the number on your screen, or you can click the chat link to our WhatsApp in the description below, and we give you the details on how you can register for online tuitions. So this is it, and we'll continue with section C. And for more of this, well, you can join us for the online tuitions. So that is it, and thanks very much for watching. We'll see you in the next video.